Okay. I'll wait till 9:30, but I basically just wanted to give you an overview of where we've been and where we're going. Did you find in the end that the review on Friday was helpful?
Yeah.
Yeah.
Okay. Okay, it's 9:30, so I'm going to start. Okay, so the first thing we did is we learned how to find components and do checks, right? So we were comfortable with looking at 2D and 3D space and looking at distances or angles and finding components and then doing a check. The next thing we did is we got comfortable in figuring out how to solve for resultants in 2 and 3D space, resultants. And then from there, we started solving statics problems, and they were statics of particles problems. And the reason why they were particle problems is because all the forces were concurrent. All the forces were converging on a certain point. So we learned how to set up the problems and then solve the problems. And I'm still conducting interviews, and I still feel like people are stuck on the steps. And if you still have an interview, please come with knowing what the steps are. And you could put them on an index card, okay? Then we just had this fun thing where we learned about pulleys. And then the next 4 things or 5 classes were all about solving for moments. Just like we had to be comfortable with forces and resultants, we now have to be comfortable with moments. Solving for moments in 2D problems using right-hand rule, 2D problems solving for it vectorially, 3D problem solving it for vectorially, and then 3D problem solving it with right-hand rule, okay? So the next step, oops. Do you see the 80% written? Oh, okay, there. Okay, so the next step now is today we're going on to a topic called couples. And then we have equivalent systems. And then we learn about all different supports and connections. And we start drawing free body diagrams of more rigid bodies. We've only done 3 rigid body free body diagrams so far. So now what we're trying to do is we're taking all these forces that were on a point and now adding other forces that are in other locations, drawing free body diagram of rigid bodies, and then solving the statics problem using the steps again. Okay? All right. Then towards the end of the semester, we have these miscellaneous topics of learning how to deal with statics problem for frames and trusses and frictions and moment of inertia and then bending moment diagrams. So where we are today is couples. And I have a suggestion and I want to ask you about it. So I'm going to stop sharing for a moment. When we did components, you watched a video and then you solved the problem based on the information you learned on the video. And then every other class we've had so far, I'm teaching you something and then you're going back and doing the homework based on what I teach you. I'm interested on this Thursday's lesson to actually flip the classroom. And what that means is you watch a video of me teaching it, and then in class, we work on all the homework problems together. And I would like to try that and see how it works, because I'm feeling when I'm teaching in class, you may not be catching everything, and then you may not be watching the video again, and then you might be having trouble with the homework and then quickly going to the solutions that I'm posting. So instead, what I would like to do for Thursday's lecture, and I've actually already taught it and filmed it myself already, have you watch the teaching lecture before Thursday, and then in Thursday, I do a quick summary, and then we work on the homework problems. How does that sound for you?
I think that sounds really good.
Sounds good.
Okay,
Yeah,
so
that's good.
I'm going to go back to sharing the screen. So we're here today in couples. I'm going to open this up. notice there's always, well, I'll talk about that in a minute. Notice under homework, it says watch the equivalent system video, and it's due on the 8th by 9:30 by our class. And you notice that Thursday's class is all on equivalent systems. So the lecture video is already here. You could watch it. I talked, when I was teaching and taping, I spoke really slow. I don't remember what the time was in the end, maybe 45 minutes. I'm not really sure. But you could speed it up if you want. You could watch it multiple times, and then just make sure that you watch it before Thursday's class. And then on Thursday's class, we're going to work on the homework problems. I'll do a summary first. But the commitment I need from you guys is that you are indeed going to watch it before class. Because if you come to class without watching it, there's no point to come to class. Did everybody hear me? You have to watch the video before class, otherwise there's no reason to come to class.
Yes.
Okay, so that's what we're gonna do. So under today, one of today's homework, besides having a couples homework, you also have watching this video. The couples homework is not due to Friday evening, 10 o'clock, but the watching the video is due before class on Thursday. Okay. So I always seem to like go straight into the problem and I mean, give you an overview, but I wanted to just show you the overview anyway. So what we're learning is in this module, you will learn about couples and how to determine the moment due to couples. Okay. So what are things you need to know? First, a couple is two forces. That kind of makes sense. A couple is two forces. They have the same magnitude, but they're opposite in direction. And the moment due to the couple is the same at any point. Not supposed to be moment. Hang on, I'm editing it. At any point in the system, and I'm going to prove that to you in a little bit. And then the magnitude of the moment due to the couple is the absolute value of the force times the absolute value of the perpendicular distance, and you find the right-hand rule. Using the right-hand rule is for the direction. And I also want to say that the perpendicular distance where the perpendicular distance is the perpendicular distance between the couple. I'm telling you what to do already, because some people have told me they really rather have an overview at the beginning, like broad scale, so that's what I'm doing. But I want you to understand why this is the case by doing a problem. So now I'm going back to the module. And here we're going to do 3 different problems, a 2D problem and 2 3D problems. But we're going to start with an example. So I'm going to stop sharing now. And I'm going to turn to the projector. Okay. And everybody knows now how to get my little screen here big, right? Okay, great. All right, so let's look at this. I have a beam here, and just so you know, a beam is always horizontal. I have a beam here that goes from A to D. I drew the XY axis. I drew a force of 50 pounds going up at B, and I drew a 50-pound force going down at C. So you could tell these two are a couple. They are have the same magnitude and opposite in direction. So they're parallel forces. And using the right-hand rule, I want you to find the moment about A, B, and D to both of the forces. So let's say instead to, due to both of the forces. So even though now we know that they're couples and I'm going to be teaching you couples today, I want you to think of it as if they're two independent 50-pound forces. And I first want you to find the moment about A, and we're doing right-hand rule. So while you're doing it, I'm going to do it too. Okay, and then why don't you look up after you do it? So remember, we're doing the 50-pound force times its perpendicular distance. Use your fingers, you get a positive. The other 50-pound times its perpendicular distance. Fingers go in direction of the 50 going down. Palm goes towards point A, and I get this value. So look up when you're finished. Isaac, can you see it? Is it too small?
I can see it.
Okay, so let's go on to moment about B. Now I'm trying to find the moment about B. Well, the first 50 goes through it, so it's not causing a moment. 50 times 2, negative 100 foot-pound.
Joanne, I have a question.
Yeah,
It says
Thank you.
using right-hand rule, find the MA, MB, and does that say negative MD?
no, it's a and
Okay, thank you. That makes sense.
symbol.
I also have a question. You said that originally in the overview it said moment
Well,
due to a couple is the
yeah, we're
same.
not gonna, Isaac, I'm sorry. I mean, I prefer to do this first, but I know some people want to hear the overview of what we're doing, the broad scale. So I introduced the overview, but now basically what we're doing is I'm proving to you what I showed you in the overview.
I was just wondering what you corrected that to, because I heard you, but I didn't see it at the time.
Oh, I wrote about, instead of writing about a point, I wrote about a moment.
Oh, okay, gotcha.
Okay. Everybody good so far? Okay, let's find the moment about D. We'll go back to the overview in a moment, okay? So from now on in class, we're going to be using the right-hand rule always on 2D and 3D problems. And you're going to get faster and faster the more problems you do. So did everybody get the same moment for moment about A, moment about B, and moment about D? Thumbs up. Maria, okay. Jordan? Okay, so what does that tell you? Oh, let me get my names.
That the moment due to the couple is the same at any point in the system.
Great. That's exactly it. Here we have a couple. We have a 50-pound force up and we have a 50-pound force down. And regardless of any point I'm trying to find the moment about in the system, a couple creates the same moment about every single point. David?
Yeah, I have a definition question.
Yeah.
Can a couple ever be concurrent? I think no, right?
It's just opposing forces at that point.
Yeah, if
There
those
you
two
go.
forces were at the same point, they would cause
No
no
moment.
change, right? Yeah.
They would cause no moment about the system. So
Okay.
yes, to first answer your question, if two forces are acting at the same point, they're concurrent, and they have the same value, they are still a couple. But there's zero distance between them, and therefore they don't create a moment. And can I give you an example?
Sure. Yeah, I mean that answered it. I just wanted to know the vocabulary.
Well, but let me just look at this anyway. Let's say I have a point here, and I have 50 pounds, and I have 20 pounds. Can everybody see that? I have 50 pounds going up at this point and 20 pounds going down. There is a 20-pound couple there, right? There's
Well,
a
wait, a
20
couple
pound,
has to be the same magnitude. Isn't that part of
right?
the definition?
But I could break the 50 into a 30 and a 20. So there is a 20-pound couple that doesn't create any moment, and I only have a 30-pound force left. Okay, that
Okay.
kind of threw you guys a little bit.
Yeah,
The
maybe
whole
my
idea,
question was confusing. I'm sorry.
what?
Maybe my question was more
No, it
misleading than
wasn't, but
helpful.
I'm trying to go to another point because this we're going to be talking about at some point in this class anyway. So if you have 30 pounds here and you have 20 pounds here and you have a 50 pounds here, I have a 30 going up, a 20 going up, and a 50 going down. I can say I have three forces here, or I could also say I have two sets of couples.
Ah, I gotcha. And then
I
it's
have a
easier to deal with
30,
them as two couples.
I have a 30, and I have a 20. Because in statics, the goal here is to simplify these problems. And when we have couples, it simplifies problems. So we're going to see this again, but does everybody understand what I did? If I have a 30-pound force going up here, a 30-pound force, 20-pound force going up at this point, and at this point I have a 50 going down, I could break the 50 into two, to a 30 and a 20, and then I have two couples in the system. We'll come back to it again. Jason?
And further, the moment is the same anywhere on the page.
And the moment would be the same anywhere on the page.
Unbelievable.
Yeah. So let's go back to this and we'll get to it more complicated. All right. So we had two forces on the system. They were both equal in magnitude, opposite in direction. And what did we learn in the end? The moment at any point is equal to what? So let's start with Laura. Laura, what is the moment due to the couple here? How do I calculate it?
You
Like note it, go back to when I calculated moment about A, moment about B, and moment about D, I found that this couple creates the same moment about any point in the system. So if I want to just look at this system and say the moment at any point is equal to, because it's a couple, I multiply what?
magnitude of the force times
The magnitude of the force times,
the distance.
right, and what's the distance?
from-
Notice it all came out to be 2. What's significant about the 2?
It's the distance between the two.
Right.
forces.
It's the perpendicular distance between the couple. So the magnitude of a moment, whenever you have a couple, you don't have to do all this work and separate the forces. You could just look at the value of the magnitude of the force, 50, and multiply it by the perpendicular distance between. And then how would I, Liam, how would I determine the direction of the couple? Take your hand. Take your hand. How can I notice that I got a negative moment every time? What should I do with my hand?
You would put your fingers in the direction of the force and turn it towards the other force?
That's right. So I put my fingers like this. My fingers are going in the direction of the force, and my thumb is going into the page. You get a negative. So let me give you some examples. Everybody could see my paper. Let's say I have a couple like this, which is what we just had. Does that lead to a positive? I'm with Luis now. Does that lead to a positive or a negative moment, Luis? I don't think Luis is here. Mackenzie?
A negative moment.
Negative. Oops, there's some eraser underneath. How about if I have the couple, the left force goes down and the right force goes up? Marcine,
Positive.
right?
But we need to know what the axes are.
What?
We
We're
need to know what that.
We're still looking at X and Y.
Okay.
I'm still looking at a 2D problem. Not until everybody gets the 2D problem do I move into 3D. But you'll see, Jason, that in 3D it's the same. Okay. All right. How about this? We are on Maria. Positive or negative?
Negative?
Yep. Say it positively.
Negative!
Yes. And Matthew.
This one's positive.
Right. Okay, so does everybody see how this is the case? So let's say we have something like this. Let me give you some other examples. Myra, positive or negative?
Negative?
Negative. Say it positively.
It's negative.
Great. And Miles. Miles, I know you're here. Positive or negative?
Positive.
Yep. Okay, so for one, is everybody comfortable with figuring out the direction? Everybody comfortable with figuring out the direction? Again, thumb out at you, positive. Thumb in, negative. Okay, let's go back to this problem. So what I learned is whenever I do statics problems from now on, I first do a quick sweep look at it and see if I have any couples. Because if I have any couples, it simplifies the math. In this case, I have a couple 50 pounds and the perpendicular distance between the two of them are 2. So it comes out to be 100 and we saw it was negative foot-pound. So at any point in this system, this couple force creates that moment. I don't have to look at each force individually. So it saves time. From now on, we're going to try to figure out how to save time in statics always.
What happens if you have more than, like you have a couple, but then you have more forces that aren't couples? Then you have to add them, right? Add them.
Great. Yeah. So let's say we have a problem where we have a bracket. We're trying to find the moment about A, B, C, D, E. And we have a 30 pound here. We have a 20 pound here. We have a 20 pound here. We have a 10 pound here. We have another 10 pound here. So everybody take a look at the problem. Right now we have 1, 2, 3, 4, 5 forces. It's going to take us a long time to figure out the moment about a point. Let's say I want to know the moment about point A. So, Peter, can we break any of these into couples to simplify the problem?
You could make A through A, B, C, D one, and then C and E another one.
Okay, talk about the forces, not the beam, not the bracket. What forces can we make couples?
The 30-pound force at B, and then the 10-pound force at C.
Okay, so we have this one, and we have one of the 10s, which means I'm crossing this out and making it a 20. Tim, what else do I have? Tim might not be here.
I don't think Tim made it.
Yeah, he has something with his head. All right, Tony, you here? Tony?
Yeah.
Okay, great. What else can we reduce?
The 20-pound force, the two 20-pound forces at A and E.
Right, right. We have this 20-pound force here. And we have this 20-pound force here. Victoria, is there another one?
You can split the 20 and then use it with the 10 at D.
Right, I have a 10, which cuts this down now to 10. And I have this. And now let me give you distances. 1, 2, 3, 4. Of course, not drawn to scale. Okay, so let's do the moment. Let's do the moment about A. So we're back up to the top, Amani. So let's treat these as couples. What's the first couple you see?
The 20 pounds.
Okay, so 20 times, I'm not going to use absolute value anymore, okay? You guys, are you okay with me not using absolute value anymore? We know it's supposed to be positive. So the 20 times, what's the perpendicular distance?
It would be 4.
4. Positive or negative?
That is gonna be positive.
Right. Did everybody hear that? I'm not putting absolute value anymore. You're going to know it is. Okay. Angel, what's another couple?
We would see the 10-pound force.
Okay. Do you want to do the blue or the red?
I would do the red one.
Okay. So red. 10 times?
1.
The red. What's the perpendicular distance? See, I know you guys are trained. I'm glad you made that mistake. I know you're trained to look at the point, but remember, we're doing moments due to couples right now.
Oh, so it would be 2.
It's at any point. Okay, so it's the red is 10. What's the perpendicular distance between the couple?
2.
2. Positive or negative?
Negative.
Negative. Bond, next one. Do the blue 10.
Yeah, the blue 10 and the distance is going to be 5.
Positive or negative?
It's going to be a negative.
Negative. So far we did 3 couples, right? And those 3 couples create the same moment about any point. But Colin, isn't there one lone force still?
Yeah, the remaining force on B, the 10 pounds.
Right, that remaining 10. So we're trying to find the moment about point A. So what's the distance?
1.
1. Positive or negative?
Positive. Sorry.
Positive. So the moment about A turns out to be, let's see, these are both negative, so that's 7, 6. So it's 60 negative, 60. I think I have plus 20.
Can I ask a question?
Yeah, of course.
So for the moment around the blue 10, wouldn't the distance from point A be 6?
Well, here's point A.
Yeah.
Oh, wait, the blue one?
Yeah.
Remember that we're doing couples, right?
Okay.
So here, it's here. Here's the blue 10, and here's the blue 10.
Oh, okay.
Here's the red 10, or pink 10, and the red 10. And here is the green 20 and the green 20. So because I reduced this to couples, so let me just start over. Originally we had 1, 2, 3, 4, 5 forces. I could have found the moment about point A due to every single one of those forces. But I could simplify the problem. Now that we're introducing couples, look, do a sweep and see, are there any couples? And you said yes. There's a pink 10, so it's 10 times 2, negative. There's a blue 10, 10 times 5, negative. There's a green 20, 20 times 4, positive. And then in addition, there's this lone 10 that's not a couple, and I have to include that. And of course, now I would need the distance to point A.
Okay, thank you.
Yeah, so at this point, you guys are, up till the beginning of class today, you're experts in finding moments. And you're not really experts yet. You're still practicing, but you know how to find, you know the process of finding moments using right-hand rule. But now you're going to start learning ways to simplify problems to decrease the amount of work. Sorry, I have to blow my nose again. I have to get somebody to clean all the dust in my house, and I don't think my kids are going to do it. Okay, so did everybody get 20? Did everybody get 20 as the answer? Yeah, okay. Okay, so what are we learning then? We're on Daniel Hall, Daniel H. What are we learning? Whenever we do, oh, Elizabeth, you got a hotspot, but on the screen it says network bandwidth is low. Let me read the rest. I'm going, and it's showing very blurry. You probably have to, you guys, how do you get it so my screen is really big? You put it in speaker view, right? Is that correct?
Pin. I use pin to your
And then
video.
you pin it. Okay, thank you. So Elizabeth, I don't know if she might have stepped out. When she steps back in, let me just write it. Just tell her to pin it.
I have a pin. I have a pin. It's just, I think that it's the network. It's not working. It just shows really blurry.
All right. Well, hopefully I'll just try to zoom in bigger. But so the point here is that if you have a couple creates the same exact moment about any point. Is everybody comfortable with that now?
Joanne, can I ask a question?
Yeah.
In this system, we're looking for it about A, but one of the forces from those couples is from A.
Good point. That's exactly where I was moving. Great idea, Maria. But look, even though this 20 goes through A and doesn't create a moment, doesn't this other 20 create a moment? And it would be 20 times 4. Right? So here, this is where I was going with this. Here we have another example. Here's a 10-pound force. The distance is 2 feet. Here's point A. Here's point B. At point A, the moment is 10 times 2 negative. At point B, it's 10 times 2 negative. Right? If I looked at point A, I could look at only this force and say it's 10 times 2 negative. At B, I could only look at this force and it's 10 times 2. Or just look at the whole system and you know that a couple creates the same moment about any point. So it's going to be 10 times 2 negative. Okay. All right, let's go on to more problems. Now I'm pulling up the problem that is in.
Sorry, what did we learn about that 20? Woo.
That here, if you find if you're looking for the moment about A, Maria pointed out that this 20-pound force goes through it, doesn't create a moment, but this 20 still does. This 20 times 4.
So does that mean that since the moment due to a couple is going to be the same for any point in the system, to find the moment of each couple, we can just
Yes,
use the perpendicular distance from one force to the other to make it really fast?
that's exactly correct. So you look at this problem, you look at the first couple, it's 20, you multiply it by 4, it's positive. You look at the pink forces, the pink couple, it's 10 times 2, negative. You look at the blue couple, it's 10 times 5, negative. And then you have this lone force that you have to deal with. And since you're trying to find the moment about point A, you have to multiply 10 by the perpendicular distance to A. So now we're going to approach a problem. So look at this problem. Do you see any couples? So Daniel I, do you see a couple?
Yes.
Give me one.
From the force D, or force 50 at D, and force 50 at E.
Great. There's a 50 couple there. David L. Another couple?
I think they're all couples, right?
Yeah,
Do you
just
want me
give
to
me
not?
another one.
Okay, let's see. The 75 force at F and the 75 force at B.
Great. David LR, another one.
The 60 Newton force at C and the 60 Newton force at G.
Great. And then Edgar?
Jesus, that's difficult. Oh my God. The 80 at A and the 80 at G.
That looks green. Oh my God, I don't have a blue marker. All right, we're doing yellow. Yellow is hard to see though. Okay. Are there any other forces here? So where, Elizabeth, do you see any other forces?
I can't see, it's still blurry for me,
Still
I'm
blurry.
sorry.
Okay, I'll just skip you. Eric, any other forces?
Yeah, the 75 Newton force at F and the 60
We already got
Newton
it.
force at G.
We already got them.
Yeah, but isn't F and G going in the opposite directions? The 60 Newton force?
Well, the 60 is going with this 60. Could you
Okay,
see
but
the
what about
colors?
the F on the other side? Just
Right,
right
this
next.
75 is going with this 75.
Okay.
This
you can't
yellow is
combine
going
them?
with the yellow. I'm hoping the color coding is helping.
It is, but you can't combine them, or you can't like double them up, I guess.
Oh, we don't need to.
Okay.
We've already simplified it. We've made it so easy. Oh, I see what you're saying, Eric. If you take the 60 and the 75, you could break the 75 to a 60 and a 50. I
Yes.
totally see what you're saying now. I didn't get it. Okay, yeah, but we've already taken care of them. We've already simplified it so much, we don't need to do it another way.
Okay.
Good point.
Do the mounting points create normal forces?
Say it again.
Do the mounting points create normal forces? or is that
We're
something-
not worrying about connections yet. We're only going to start looking at connections on Friday.
Excellent.
So we're just looking at the free body here, this free bracket. So in the end, we only have moments created. Well, no, I'm sorry. Let's jumping ahead. We only have couples, right? Everybody agrees? Okay. So now, Gerardo, because we have an 80 going up and an 80 going down, a 75 going left, 75 going right, 50 going up, 50 going down, 60 going to the right, and 60 going to the left, what is the resultant force in this system?
0.
Right. Right? Couples create no resultant force because all the forces cancel out. But what about the resultant moment? Let's find out the moment that's created by this system. So Hyoji, let's look at the 80. So the moment is equal to, so 80 times, what's the perpendicular distance between the 80? Yoji, are you here? Okay, Isaac?
Perpendicular distance between the 80 is, that's a lot of addition.
Right. I got 650.
Yeah.
You know, you
Whatever all
guys,
those add up to.
think whenever you have things in quarters and stuff, think in money. Money. Look, you have $200, $300, $400, $500, $600, $650. You know when it's money, you add it faster.
I don't know. My money doesn't add up fast.
Yeah, well. Okay, negative or positive, Isaac?
That is going to be negative.
It's the money you want. It's not the money you have. Okay, next, Jack. Let's do the 75. What's the perpendicular distance? Jack, you here?
Can you raise up the paper?
Yes. Okay, I don't think Jack's here. Jason.
What do we
If I raise up the paper, then you can't see the numbers.
That's true. So we're multiplying by the 75. So we're looking for the perpendicular.
Hang on a second. Hang on. We already know the resultant force is 0.
That's right, because all of the forces are couples, and so there may or may not be a moment. And
75 times.
that, we're looking for the perpendicular distance between the 75-pound forces, which I see is 125 millimeters.
Great. Positive or negative? Positive or negative? Jason? So the 75 is going to the right on the bottom and going to the left on the top.
Positive. Oh, sorry, I was muted. I said I'm looking for my axes. I found them. I say positive.
Positive. Okay. Next one. Jason Lee. Let's do the 60 pound.
Yes.
Actually, it's not pounds at all. It's newtons, isn't it? So how about 60?
60, you're going to add 125 to 200. That will be 325.
Positive or negative?
It's going to be negative.
Right. Okay, how about the 50? Jordan.
The 50 would be,
What's the perpendicular distance between the 50s?
225.
Great. Positive or negative?
Negative.
Right. Did I miss out on any? Look, must be. 80, 75. Wait, 1, 2, 3. No, I guess I got them all. 4. Okay, and it comes out to be negative 73. Sorry. 400, and it's Newton millimeters.
You didn't have to specify a point. We just said M because it's no matter where in the system, it's the same.
Exactly. Did everybody hear that? I did not put a subscript for M because there are only couples. Because there are only couples, the moment that's created by couples is the same at any point. The moment about A or B or C or D or F or G or E, they all have the same moment. Cody. Laura. Why did I not have to specify the point? Hang on, Miles.
Because the moment is the same at any point.
Right, because it is only couples. The moment's the same at any point. Miles, what's your question?
Yeah, so that doesn't really make sense to me, because if I take like a simplified case of like say like one line with 10 pounds at each end, one going down and one going up, the moment along that line wouldn't be the same for every point, right? Because it would be 0 in the middle, but you would have
Why would it be 0 in the middle?
Jason, be quiet.
Oh, sorry. No.
Miles,
Yeah.
Miles. So
Oh,
I
yeah.
just-
So you would.
Right? Okay. So Miles, in this case, first of all, one thing you said is the moment about the line. And there is no moment about this line. This line is not
right.
spinning, right? You're trying to find it's an XY problem. So the moment's only about the Z, and we would be finding a point. It's the moment about Z of any point. Okay, it's not of this line. All right, but I think you cleared up your question.
Yeah, so it's literally wherever you go, it's the same.
It's the same moment at any point here.
Trippy. Okay,
Yeah.
thank you.
So one thing I didn't do here, though, what should I have done? I didn't tell them the direction. I have to put a K in here, or I have to put a Z here. I have to tell my direction. Did everybody see that? I left out the direction of this moment. It's in the X, all the forces and the distance are in the XY plane. I have to say where my moment is. And I could either say moment of the Z, about the Z axis, or I could put K in here. I have to do one of them. Does everybody hear that? I want to hear it loud and clear. Everyone, yes? Yes.
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 Okay, good?
Yes.
So what's the proper way to say that in words? You'd say like the net moment of this system is this number, or what's the way to talk about
I
it?
would probably just say moment about any point is negative 73,400 in the Z.
Okay.
Can you
Use
say-
moment
Or you
about
could say
any
this,
point.
the
All right.
moment about any. The key is, and when you're an engineer, you're always going to need to know what point you're trying to find a moment about, right? And the idea is, so if the question said, well, what's the moment about C? Well, yeah, but they're all couples, so you just calculate them quickly. You don't have to do everything about point C. So what's most realistic for us to happen is a problem like this, where we have some couples and some not couples, and we're still trying to find a moment about a point, but because there are couples there, it simplifies the math, the work. Okay, so now we're moving to a 3D problem.
Can I
Oh, wait,
ask
before,
one more
wait.
quick-
Yeah, Isaac?
That thing you said right at the bottom where you circled Z and K, could you say that one more time?
Yeah, so if I just say M equals, I'm not telling the direction. I'm giving the magnitude of 73,400. I'm also giving a negative, so I know how it's going to spin counterclockwise, but I didn't specify what axis it's spinning about. This is a 2D problem. All the forces and the distances are in the XY plane. I have to specify that the spin is about the Z axis.
Now, but if we would specify that by putting K at the end, yes, but if we put a subscript, doesn't that make it look kind of like we're saying this is about some random point Z?
Well, no, we're accepting that this is about the Z axis. I guess, what, you want to write Z axis? I guess you could write Z axis. But I'm okay with this or this. I just need to know it's spinning about the Z.
Gotcha.
Okay. Okay. The important thing too in this problem is, you guys, this is new to you. And I'm going to introduce it as new to you for equivalent systems too. The word resultant, the resultant in the past always meant resultant force. Would you agree? Resultant, the term resultant to you always meant resultant force, because that's what you were always finding, forces. But the term resultant to us now, it means, how is this thing moving? What is the resultant linear movement? What's the resultant rotational motion? So resultant is actually an adjective for both force and moment. So if I said, where are we? We're at, Laura, I think we're back at you. Laura, if I ask you, what is the resultant of this system, what would you numerically tell me?
It is negative 7,400 millimeters.
Right, negative
B direction.
7,300, 400 Newton millimeters moment, right? Because when I say what is the resultant, you're telling me that the resultant moment is this. What is the resultant force in this problem? Laura?
Zero.
Zero. Okay? So when a statics, from now on, when the statics problem says what is the resultant, you have to give the resultant force and the moment. Okay? So if a problem says, what is the resultant of this system? Sorry, if a problem says the resultant of the system is 10 pounds, did everybody hear that? The resultant of a system is 10 pounds. What do you assume the resultant moment is? Zero. I see Maria giving me a zero. If the problem says the resultant of this system is 10 pounds, it's telling you that there is no resultant moment. It would be awesome if a problem said the resultant force is 10 pounds and the resultant moment is zero. That would be wonderful, but you're not going to hear that. You're going to hear the resultant is 10 pounds because now resultant means force and moment. Okay? So now we're going into a 3D problem.
I have a question.
Yeah.
Why couldn't that be referring to the resultant moment and there is no net lateral force?
Different unit.
We could. I could tell you.
How is it a different unit?
I'm sure you said pounds, and moment would be pound.
I said pounds.
Foot pounds.
Oh.
Foot pound. God, thank you. That clears it up.
Thanks, David. Okay, so I have a question for you now. It is 20 after 10. I have two more problems to do, and they're both in their 3D problems. But we're planning on taking the quiz at 10:30. So we have two options. Either I continue teaching and you take the quiz after class on your own sometime, or you take the quiz now and I video doing this. I think you should take the quiz now. I prefer you to have video the quiz in class.
Why? Why?
Because
we lose the interactivity of the teaching.
But we can slow down the we can slow down the video.
That's true. That's
you can slow down the video. It's very important to me that I am able to assess what you know and what you don't know, so that when I see what you don't know, I know what I have to concentrate on and I know who to meet with outside of class. And if I give a quiz that you have a long period of time and you could talk to each other, then I might not be getting a quiz back that's representative of what your skills are. And I am concerned about that. And it's not that I don't trust you, it's just that I want to make sure. Anyway, so what do you guys, I mean,
Read
so
the chat.
I'd probably rather you take the quiz.
The vote in the chat is mostly live lecture.
All right.
I have physics. I don't know about anyone else. I have physics lab directly after this, so I won't be able to do it till like way later. I'd rather do the quiz now.
I got an idea. How about those of you who want to do the quiz now at 10:30, do the quiz now at 10:30, and you watch my video. And those of you who want to stay for the live teaching right now can stay for the live teaching, so we could do both.
Great idea.
Good? Okay, because some of you have physics and some of you have stuff going on. So that's what I'll do then. So those of you who want to do the quiz now, you're going to get off the screen now, and the quiz will be ready at 10:30. It'll be open. And you have until 11:15. And then remember to make sure that you're taking the quiz. So Laura, you're going to take the regular quiz that starts at 10:30, not the one that has your name on it. And then all the ASC students will take the other quiz that says ASC. And then those of you that are staying live, stay with me. And then at the end of the live lecture, then I'll have to find out from you guys when I could open the quiz. Or rather, those of you who are staying in the live lecture, I'll open the quiz at the end of class, and then I'll give you the amount of time you need. Thumbs up for everyone? Okay, so those of you who are going to get off now to go take the quiz, you could get off.
Thank you, Joanne.
Yeah. Okay, so everybody left is staying, is that right? And could I see you all, please? Put your faces on. Okay, great. So you guys are all okay, then you're all staying on, and you're all okay taking the quiz when class ends at 11, yeah? Okay, great. All right, so we're moving on. Let's take a look at this. So I'm just gonna go around the room now because I see you guys. So David, do you see a couple here? Tell me a couple.
Yes, I think there's 3.
Okay, well, give me one.
Okay. Yeah, you're hovering over the 100 up, and then also the 100 pound up in the front there, and then the 100 down in the back right.
Okay. Jason, give me another one.
Oh, I see there's an 80-pound force in both. Yeah, going in both directions,
Great.
perpendicular distance. Yeah, it looks like 80.
Matthew?
There's the 150 pound in the
Great.
Y direction.
Great. Mackenzie, are there any lone forces? Oh, I can't hear you.
No, not that I see.
Everybody take your, just take your mute off. Okay, no. So that means the resultant force is what, Mackenzie?
0.
0. Okay, now we're trying to find the resultant moment. Okay, so we're going to do this, the resultant moment. All right, so Edgar, start off with you. Edgar, look at this 80-pound force. What is the perpendicular distance between it?
Okay, so the forces are going the x direction and they're lie in the xy plane. So that means the distance 8 inches.
Excellent. Okay, now ready for the other complicated part. What axis is it spinning about, and is it positive or negative?
It's in the c-axis and it's negative.
Excellent. Okay, David, LR.
Yeah.
Let's do the 150. What's the perpendicular distance?
6.
Excellent. You guys are doing great. What is it spinning about? Which axis?
It's negative and spinning about. Let's see.
Yep. I was a little hesitant there, but it was correct. Okay, Maria, you ready? I think she stepped out.
Wait, I'm back.
Okay, stay here. Okay, you got the really complicated one. Look at the 100. What is the 100 spin about? Well, first of all, what direction is the 100 in? X,
It's
Y,
in
or
the-
Z?
It's in the Z direction.
So can it create a moment about the Z?
No. 'cause it's
No.
very-
Does it create a moment about the X?
No, because it intersects with the x-axis.
Remember though, only one of them intersects. This is a couple,
Okay.
right?
Yes.
It's not just this x-axis, it's any x-axis anywhere. Does it create a moment about the X?
Yes.
Yeah, so it's 100 times. What's the perpendicular distance to create a moment about the X?
Hold on. I think it's 12 inches.
Okay,
No,
so let's figure this out. The force is in which direction?
it's in the Z direction.
Z. I'm trying to find the moment about the X. So the
then-
distance has to be in
okay. It has to be 16. It has
correct.
To be
So we're finding it in the, and does it create a negative or positive moment about the X?
it creates a negative moment.
Excellent, and you're gonna keep going.
Okay. Wait, hold on. I have a question. It doesn't create a moment about the Y?
I'm going there now.
Oh, okay.
You got the next question. Does the 100 create a moment about the Y too?
Yes.
Yes, 100 times, what's the perpendicular distance?
Now it's really 12 inches.
Right, because the forces are in the Z, we're trying to find the moment about the Y, and the perpendicular distance is in the X. Positive or negative?
It is going to be negative.
Negative, J. Okay, so for this pink one, you guys, if you're trying to find the moment about the X, look in this direction. Look in this direction, and 100 is up on the left, and it's down on the right, and it creates a negative about the X. Then, and I shouldn't put an arrow, let's put an eyeball. Does that look like an eyeball? I'm looking in that direction. Now, when I'm trying to find the moment about the Y, I'm looking in this direction, and the 100 is down to the right, and the 100 is up to the left. So now, the moment equals negative 1600I minus 1200J minus, what's this, 64? I think I have the math somewhere.
Be 640, I think.
$15.40. Well, actually, I have $15.40. You guys do the math. Did somebody get $16.40?
$15.40.
1540.
$15.40. Okay. And this one's in the K, and all the units are in inch pound. And this is in vector form, right? But how else do we represent moments? Now I'm in Gerardo. Besides representing a moment in vector form, how else do I have to represent it? Gerardo?
Hi.
Besides representing the vector, a moment in vector form, how else do I represent moments?
In magnitude and direction.
Right, and direction angles. I'm not going to do it, okay? Because I want to do the other problem. Okay, any questions on this? It's hard. You got to see it in 3D. Two of them weren't too hard because they only created a moment in one direction. But that last one, that 100-pound, created two moments. Okay, now we're going to another 3D problem. Okay, Angel, tell me all the couple, are there any couples here?
There are some couples.
Tell me them.
There is the 75-pound couples from C and E.
Right? What else?
There are the 100 Newton, I just realized they're Newtons, not pounds. 100 Newtons at D and E.
Okay.
And 80 pounds at A and B.
Okay, are there any other forces?
There appear to be no more forces besides.
So what's the resultant force?
We have 0 resultant forces.
0, and you guys got it, right? All the couples cancel each other out. So now we have to find the resultant moment. Gotta do it in pencil. Okay, we are at Jack. So Jack, the 80. Let's do the 80 first. And can everybody see the axes, right? This is X. This is Z. And this is Y. Jack, you here?
Oh.
Yeah, I'm here.
Okay, Jack, so that we're looking at the orange 80. So give me a perpendicular distance between the two 80s.
375.
Great. Say it with confidence.
375.
80 times 375. The 80 is in the X direction. The 375 is in the Y direction. So what moment, what axis does the moment, does that 80 times 375 cause a spin about?
It'd be in the Z.
Correct. Positive or negative? It's hard to do, huh? Put your thumb in the positive Z. Does it create this spin? It does.
Yeah, okay.
Try putting put your finger in the negative spin. Does it create it that way? No, it's positive.
Oh, okay. Yeah, when it gets 3D, I get slightly.
Yeah, it's hard. It's going to take a long time. Okay, Jack. Now what's the other perpendicular distance between the 80s?
250.
Right. Nice confidence. So now the 80 is still in the X. The 250 is in the Z. What's the moment going to be created about?
About the Y.
Y. So put your thumb in the positive direction of the Y. Does that 80 up on top to the left create a positive or negative?
Positive.
Right. Any questions on the 80? It may be.
I'm trying.
Yeah.
I'm trying to find the sign for the first term, your X
Okay.
term
So,
of the moment.
So on this one, put your eyeball looking in this direction.
Okay.
Oh, I'm sorry.
It's a
Sorry,
Z,
Matt.
right? It's a Z
Yeah,
moment.
it's easy. I'm sorry. Put your eyeball looking in this direction. Going down, it's spinning this way. In order to spin this way, my thumb's got to be in the positive Z.
But I thought our palm would face the axis in question.
Ah, okay. So no. Good question. We're not looking at the palm anymore. Because it's 3D, the only thing we're looking at is our thumb. Because the palm would be really confusing, especially in a couple, because there are two different forces. I'm so glad you asked that question. Because now we're entering the realm of couples, we are no longer putting our fingers in the direction of the force. If this is, remember, if a couple is like this on the Z, it's creating a positive. If my couple is like this in the Z, it's going the other way, sorry. It's negative. So the way to determine right-hand rule for couples is no longer dealing with your palm because there are two different forces. It's confusing. So looking down from the Z, when I look down from the Z, I see this. Jason, when you look down from the Z, do you see this or this? A or B?
A.
A. So it's positive. Let's try it. Let's do this 8250. We're still looking at this. I'm looking down from my Y. I'm looking from my Y. This we know is positive. This is negative. Do I have this or this? Looking down from my Y.
At what
Do
force?
I have
The 80s?
C or D? Which one,
We're
Jason?
looking at the 80s again.
We're still looking at the 80. We're looking at the ones we just did.
Very well.
So if we look at the 80, or was it C or D?
C.
C. So I'm going to repeat that. When we are doing right-hand rule with couples, we're determining whether it's positive or negative based on the directions that these two forces are in relationship to each other. Okay?
Jason, I did a little sketch a while back of like those different directions. I don't know if this might help you out.
Yeah, let's see.
Let's see, it's tough for me
Oh,
because
yeah.
of the camera, but so, and my Y is going up, but you can see it's like what direction around that axis is what we're talking about, and what direction around that axis we're talking about, and what direction around that axis we're talking about. I don't know if that's helpful. John, just make sure
Yeah.
that's right first, I guess, but I think.
Yeah, no, I think it's great.
Okay.
And
Do it.
David, this is specifically with couples.
This is
finding
just the
moment.
notation of how we talk about moments, right? And so.
Oh. Yeah, I am comfortable with that aspect. I appreciate that.
Okay. So I think I was also trying to get my head around your question. I think you might be overthinking it. It's just which direction around.
I've never
each
heard that before.
axis. It's just which direction around each axis, right? So if the couple is spinning clockwise,
That's a great way of saying it.
that's negative, and if it's spinning counterclockwise, that's positive.
That's a really great idea. Look at it as a top. If we're
Yeah,
if the 80, if the is the 80 creating a counterclockwise or a clockwise spin around Z? So it is creating a counterclockwise spin around Z, so it's positive. I think that's a really great way of thinking about it.
All right.
So for the 80 with Y, the 80 is creating a counterclockwise spin around Y, so it's positive.
And what
So
I'm
you could
seeing
think-
on this one is you also like what we've seen before. Like, so the orange one has no X component, right? Because it goes along that, both of them go along that axis. Is that a good way to think about it?
Right, this force is in the X direction, so it cannot create a moment about the X.
Okay.
So then
And
the
so-
question is, does it create a moment about the Y and the Z?
Right.
Can I go back to our other 3D problem? Here, look at the 150. The 150-pound force goes in the Y direction, so it cannot create a moment about the Y. So then, does it create a moment about the X? Well, it's actually parallel to the X. Or the way Jason wants to say it, or David, is that the 150 lies on the YX plane, so it can't create a moment about the X, but it can create a moment about the Z. Let me say that again. This orange 150-pound force is in the Y direction, so it does not create a moment about the Y. So there's a potential for it creating a moment about the X and the Y, X and the Z. It does not create a moment about the X because it's parallel to the X.
Perpendicular
Or-
to the X? Wait.
It's parallel
To X?
to X, to the XY plane.
Oh, to the plane. Okay, to the plane.
To the plane or a line. I mean,
Well, it's perpendicular to the X-axis.
Yeah.
oh, okay, I'm looking at the planes.
Anyway, yeah, that's okay. Sorry, that's
Okay,
that's
no, I see
pedantic.
what you're saying. The force, yeah. The forces are on a plane that's parallel to the
Yeah.
X-axis plane.
Okay.
Well, no, there is no X-axis plane.
XY plane.
XY plane. Yeah.
Yes, there is an XY.
Okay, all right. But I guess it's better to say maybe the forces are perpendicular to X. Let's think about that more on the next problem.
Sure.
But it can create a moment about the Z. So on this problem with 80, The 80 is in the X, so it cannot create a moment about the X.
So now I'm back to wondering why that first term isn't 0.
Which
Well,
one?
it is. This is 0, but this is still creating a moment about that.
Your I term down, if you scroll down. Oh, that says K.
K, yeah,
Oh,
it's spinning
Not creating a
around.
moment
Oh.
about this, but
Z.
what you're saying is the Z. For the Z, you said, Jason, that the 80 intersects the Z, so it doesn't create a moment, but this one does. You
Sure.
have to not look at these individually. Once you deem that you're working with couples, you have to look at them together.
Okay.
I feel like we might be making it a little bit more confusing. Can we go back? So Dave, now David, I want to look at the 75.
Okay, sure. The
75 is in what direction?
Yeah, so the 75s are going along the Z-axis, so there won't be any Z.
Right.
I
So there's the
believe they will
potential.
have both an X and a Y.
Okay, so now let's just do the problem the way we did before. Give me a perpendicular distance between the 75s. Give me one perpendicular distance.
Sure. One perpendicular distance would be 375 millimeters.
Right, 375. The 75 is in the Z. The perpendicular distance is in the Y. So that means the moment is about
That's about X.
X.
It's a
view it,
positive I.
and if you view it going this way, it's creating a counterclockwise spin around I, and it's positive if it's counterclockwise. Okay, David, the next one. What's the other perpendicular distance between them? Still
They'll
the
only be
75s.
100.
Oh, okay, we'll go to the other David. David, or
200.
David Leopold.
Yes.
From now on, I'm going to call you Dave.
I intentionally changed my name for that.
Okay. Where you were David in Engineering 5. So now you're Dave. Okay.
I'm sorry, yeah.
That's okay. David, what's another perpendicular distance between the 75s?
200 millimeters.
Right. What axis does that moment create it about?
About the Y.
Excellent. How come?
The distance is in the X.
Right.
And the force is in the Z.
Right. And does it create a positive or a negative moment? How does it cause the y-axis to spin?
Counterclockwise.
Put your thumb. Put your thumb in the positive y? Does it do it that way? Does it spin in the with the thumb in the positive y, or does it cause a spin with the thumb in the negative y?
I'm not sure.
So take a look at the, if you're looking at it, you're looking at your eyeball here, right? The force is over to the right behind it, going down to the right.
Oh, it's this way, the negative way.
Right, because take a look, here's the y-axis. I have a 75 coming up on the left side, and I have a 75 coming down on the right side, and it's causing it to spin with my thumb in the negative.
Okay.
Is that helpful? Take the axis, and this is on the left, this one's on the right.
Mm-hmm.
Okay?
Yeah.
All right, we're up to Maria. No, Maria, you already did one, right?
Yeah, but I'll do another one.
Let's have Mackenzie. So let's do the 100 now. So the 100, give me a perpendicular distance between the 100s.
200 millimeters.
Great, 200. What when you multiply 100 in the y to a 200 in the x, it creates a moment about what?
The Z.
Right. And is it positive or negative? Look at the z-axis. This 100 force is behind it, and this one is in front of it. Does this help? Does this drawing help here?
Yeah, so it's positive.
So this one is kind of behind it, and this one's in front of it. It's, what is it, positive or negative?
Positive.
Do it again. Put your fingers, in order for it to spin around the z-axis like that, my thumb is pointing down.
Okay.
So it's negative. Okay, let's do the other one. What's the other perpendicular distance between the 100?
250.
250. Okay, and that, the 100's in the Y, the 250's in the
The Z.
Mackenzie?
The Z.
So we're finding a moment about which axis?
The X.
Right. Okay, so now look at the X. The 100, the top one is up here, and the bottom one is underneath. Is that a positive or a negative spin around the Z? Actually, I should have drew it. I should draw it better. If this is above and this is below, so let's draw it below. So it looks below. Positive or negative, Mackenzie?
Positive.
Positive. So the resultant moment comes out to be, and I have it here.
Wasn't that for the 100 Newton force?
What?
Was that for the 100 Newton force?
Yes. Oh, you can't see where I am. I'm gonna pull this down.
And you got a positive about X for that?
Oh, I drew it wrong. Shoot. Thanks, Jason.
Sure.
Okay, Mackenzie, sorry.
Okay, so it's negative.
Yeah, see this force is to the right. So the top one is, the top one is to the right and the bottom one is to the left. Sorry, so it's negative. Thank you. Okay, so the moment the answer comes out to be, and I'm going to convert it to Newton meters. 3.1 I plus 5.0 J plus 10.0 K Newton meter. So we're introducing a few topics. One is now couples, right? When there are two forces, same magnitude, opposite direction, they're couples. And they simplify the problem because in order to find the moment on the system due to the couple, it's only the value of the couple, the force, times the perpendicular distance between the two forces. And then you have to find out whether it's positive or negative based on how it's causing the axis to spin. So whenever you get a statics problem now, do a quick look. Is there a couple? If there's a couple, it's going to simplify the problem. You could right off the bat find the moment due to that couple. If there's a force other than a couple, well, then you still need to know the point you're finding the moment about. Another thing, what other things did we learn? We learned that the word resultant now doesn't just mean resultant force. We started in statics with resultant meaning forces, but now it's the resultant on the system. So if we look at this problem, what is happening to this box due to this couple? Edgar, what is happening physically to this box due to this, all these couples?
Oh, can I see just the final resultant moment?
Sure.
Well, it's kind of hard for me to say, but it seems like it's gonna have the tendency to rotate.
Yeah, that's right. So the answer that I was looking for is it's spinning. This body is not moving side to side. It's not moving linearly because the resultant force is 0. It's just spinning. And if we find the magnitude of this moment and the angles, we know how it's spinning, right? And we could do that. Let's draw it. Here's my x-axis. Let's see. This is Z. This is Y, and this is X. What is happening here? Well, we have a positive moment in the X. And it's 3.1 Newton meter. Did I draw it in a positive way? The Y has a positive. It's 5.0 Newton meter. And the Z is negative. Sorry, it's positive. Positive 10. So it's spinning in the X. It has a component of spinning in the X, has a component of spinning in the Y, and has a component spinning in the Z. And it's all positive. So which way is this resultant moment directed? Edgar, you want to still do that one?
Could it be like in the first octant?
The first octant. So if I direct it in the first octant, my thumb is in the positive direction of the pen and it's spinning counterclockwise. So it would be as if my top, which is here, is off at an angle and it's spinning counterclockwise. So think about this. We're learning about what possible movement something can have due to forces. Previously, when we did resultants at the beginning of the semester, we calculated the resultant force, meaning we learned how much it was trying, the forces were trying to make it move in all three directions, linearly. Now these forces, on a particle, right? Now these forces are trying to make this body spin. In the end, in statics, we're trying to prevent motion, right? So we're going to calculate what the forces are in connections, like Isaac had asked. What is going on in these connections? What do these connections have to resist? In this problem, we had a resultant spin, a resultant moment of negative 73.4 Newton meters. These forces are trying to take this bracket in the negative direction and pull it off the connections, right? These forces are, their intent isn't to break the connections. But you as an engineer have to design and choose the type of connections to have to withstand the forces, withstand the motion, whether it's linear or translational, so this bracket doesn't go flying and hit somebody in the head in a factory, right? So for us in statics, we're going to calculate all the forces and or moments that this pin must resist. And then when you get to engineering 40, strength of materials, you're going to choose the type of material and how big the material is to withstand that force in motion. Does that make sense? So I know these are pin connections. Pin connections cannot withstand a moment. You ever have a pinwheel? You know those things at the fair that spin around and you blow them? It allows a motion right? I can't break a pinwheel by creating too much force in motion, in a rotation. But I can break a pinwheel if I push it too hard in the X or the Y. So we need to know, if you get a pinwheel, you want to know, what is that strength in that pin? What force could it actually withstand? And you know that the thicker the pin, the more load it could withstand. And the stronger the material can make it withstand something. So you pick a steel pin, it's going to withstand more than an aluminum pin, but then the steel is going to rust and maybe disappear, because when something corrodes, the material just degrades. So as an engineer, you have to decide, what kind of material do I want to make that pin out of that it's not going to break and not going to corrode? So you're probably going to pick aluminum. You might pick stainless steel, but then it's more expensive than aluminum. Or you might pick some alloy that's really cheap,
You ever
right?
seen aluminum in the ocean?
What?
You ever seen when they put aluminum down in the ocean?
Well, it does corrode. It gets
corrodes.
it gets a protective shield on it that turns white. So if you look at aluminum, it corrodes, but it becomes this protective shield. But certainly now, if you put it in an extreme environment like the ocean, eventually it's going to fall apart too. But we're going to assume that a kid is not going to drop their pinwheel and leave it in the ocean. And if they are going to leave it in the ocean, they're never going to get it again. So who cares if it breaks? But we're more concerned with the moisture in the air. So steel is more of a problem than aluminum. Good point though, Jason. I loved teaching materials, but Carl teaches it now. Maybe sometime when he takes a sabbatical, I'll get to teach it again. But in any event, that's where we're going. We're trying to figure out, what motion does these forces create? And is that motion a linear motion or a rotational motion? And then we look at the connections and say, okay, well, what forces and moments do these connections need to resist? And once I know what it needs to resist, then I can design the connection. The extent of statics is to find out what these guys need to resist. And then in strength of materials, that's when you design the material, design the connection itself.
Very cool.
Yeah, it's really neat. Okay, we good?
Quiz time for us, I guess.
Yeah, that's it. So I'm not gonna, I know I went over 20 minutes, but I'm not gonna give you the 20 minutes back because I think you wanted to hear all that engineering part. Okay?
That's fine.
Okay, great. All right, so I'm gonna post this now, and now I'm gonna turn your quiz on. How do I do this? Well, the quiz is on now already, right?
Can you just change like the due time? Can you make it due at
Yes.
11:30?
Yeah,
By
I'm gonna
11:30?
change the due time to 12:30. I'm just gonna change it to 12:30, so I only have to change one. Okay? I'm gonna go do that now. Okay, see you guys.
Cool. Thanks a lot, Joanne.
Bye.
Thank you, John.
Yeah.
Joanne, could I speak with you?
Thank you, Joanne.
Let me stop the recording.